Hi everyone, welcome once again to Learn Math with me, Brian Sapinski. Now, last time out, you saw me, my daughter Brianna, and her friend Maria playing the Deal or No Deal arcade game during our trip to Lake George, New York. You must visit there, by the way. In that video, we talked about the mathematics of averages and percentages that the AI of the machine bases its offers on. But in preparing that video, I got curious about something else, and that's what this video is going to be based on. See, at the start of every game of Deal or No Deal, most machines are programmed to show you the contents of all 16 cases, and then they shuffle them around for 7.25 seconds. I actually checked. The hook is for you to try to follow the jackpot case as it gets swapped and spun around, and then choose the number of its final resting place. Now, it is a hugely difficult task because the pace that those cases move around is crazy fast. So if you can do it, hey, more power to you. Now, as you watch the shuffling, you notice multiple ways that they move the cases around. Sometimes they pair all the cases off and switch them with each other. Other times they shift them all in a circle. They can even do both in some combination, make switches and spins in multiple directions, or even leave some of them stationary for a split second while others keep moving. Again, it's very confusing to keep track of. But my curiosity and the focus of this video has to do with the first type of shuffling, the pair swap. The question I was asking myself was this: if you take all the 16 cases and swap them two by two all at the same time, in how many different arrangements can they be switched around? Now, at first, I thought that maybe this was a power scheme. We're dealing with sets of two, there are 16 cases, and 16 happens to be a power of two. So perhaps the number of arrangements would itself be a power of 2, like 16 or 32. But I honestly didn't know exactly how to spell out the calculations that would prove that. So I went and did the fun part instead. I drew it out. I took a 4x4 grid, circled all the adjacent pairs, and tried to maneuver those pairs in every direction I could visualize. And after my modeling effort was all done, I wound up with a total of 36 arrangements? Okay, now I was really confused. Did I make a mistake? Did I repeat an arrangement? Did I forget any? Because if I passed 32, I was sure that I had to get to 64 for my power of 2 prediction to be true. But nope, by all counts, 36 was my final answer. So just how was I supposed to calculate the solution that I'd found now? After a lot of asking around, a friend and math teacher out in California, David Hammett, helped me find the answer to that question after he himself was initially stumped by the problem. He found a PowerPoint presentation that I have put a link to in the description below. Now, it is extremely long and involved in more ways than one, and most of those ways go way beyond the things that I will likely ever look to accomplish on this channel. The one part I can discuss here to a small extent is that it involves calculating a determinant. Determinants involve the use of a square matrix of numbers, and they serve many purposes, again, many of which are beyond the scope of this channel. The smallest square matrix that requires a determinant formula is a 2 by 2, and at least that's easy to calculate. Assigning the names A, B, C, and D horizontally to the four entries in this matrix, the determinant is calculated as the product of A and D minus the product of B and C. So for instance, in this matrix, we would multiply the 2 and the 8 together, and then the 4 and the 6, subtract them from each other in that order, and get a final determinant of -8. Now, working with matrices and calculating determinants usually happens when you get to algebra 2. And calculating 2 by 2 determinants, like the one we just did, is a piece of cake. You'll also likely calculate 3 by 3 determinants, which start to get a little involved, but they're still well within the realm of accomplishment when you're first learning them. Sadly, the matrix needed to solve our deal or no deal problem is not one of those simple ones. In fact, as you'll see in the PowerPoint I mentioned down below before, the solution here requires not a 4 by 4 matrix, which you would think it would since that's how the deal or no deal cases are arranged, but an astounding 8 by 8 matrix. The The reason why involves, among other things that are a little complicated at first to read, a combination of networking with minimum spanning trees and map coloring, which I will discuss in a series of discrete math and statistics videos further down the road in the life of this channel. Using those skills, you end up creating an 8 by 8 matrix consisting of an assignment of zeros, ones, and negative ones, which are then placed through the determinant formula. And by the time you get to an 8 by 8 matrix, this formula is so insanely long, you might think the only thing longer is all the banter I've done in this video. But in fact, when it's all said and done, the determinant shockingly came out to exactly 36, which means that my puzzle modeling was right on the money the whole time. Now, I wouldn't even dare try to ask you to duplicate that process or do similar for any other size matrix for that matter. But hey, more power to you if you want to go for it. Instead, I want you to have the same fun that I had in preparing this video and a little bit more. I challenge you to come up with the same 36 shuffling arrangements that I came up with in my pencil and paper work. Now, you saw some of them already during the course of this video, so you got a little bit of a head start. It's now up to you to see if you can come up with the rest. Now, if you think you found all 36, I want you to scan a picture of it and email it to me at brian.sapinski@gmail.com. And if you're right, I will grant you the ability to choose any elementary or high school math topic for me to address in a new video later on down the road. So the power is in your hands. You can help dictate what you see on this channel in addition to my regular work. And while we're here, we've been talking about the follow the case thing with deal or no deal the whole time. I'd be kind of remiss if we didn't actually play it. I mean, we're here. That's the whole point of the video. So let's do it. At the end of the video, I'm going to show you 16 cases. I'm going to show you the contents of each one. And then just like the arcade machine does, I'm going to shuffle them around right there on the screen. And I'll use some of the 36 shuffling arrangements here as well, along with some of the other techniques that the arcade machine actually uses. And when it's all done, pause the video and see if you can identify where the jackpot case ended up. In fact, when it's all over, I'll even show you the answer so you can see how you did. And leave me a comment below this video and let me know exactly how you did. Did you find the jackpot case, or what number did you actually end up with? So, hey, let's all play along together. I want to see how skilled you are actually in trying to follow the cases. You got to be better than my eyes are, that's for sure. So look for that at the end of this video. In the meantime, before I do that, again, a quick thank you to David Hammett out in California for his help in researching the math for this video. And please make sure to like and share this video so that more people can play, because I want to see what a lot of you can do with this. And of course, subscribe to this channel for more math and fun in the future. And hey, who knows, if a lot of you like this follow the case game, maybe I'll make some more of these in the future. So let me know, but for now, let's do this one. Let's play Deal or No Deal.